initiates the breaking of the carbon bonds. By heating slowly over a period of years, you allow hydrogenation reactions to occur in the kerogen itself. And so you're doing a lot of the work that a refinery would normally do over like 30 minutes with a catalytic cracker. But here we're hydrogenating over several years, and we're doing it at a much lower temperature. And then we're distilling out only the light products, so we're leaving the heavier products behind, and they coat. And we're able to change the product quality on the fly. That is, it's controlled entirely by the heating rate and the pressure. By heating slower or faster, by raising the pressure or lowering the pressure in the subsurface, we can make a better product or a less good product, but more of it. Okay, so the kerogen basically starts breaking down to bitumen, and then the bitumen itself breaks down to oil and gas, and the carbon residue, about 25%, stays behind the rock. And the product suite that we make is gasoline, jet, and diesel, as well as natural gas and hydrogen. Here's some reactors at Ben-Gurion University where we simulate the process. You can see some of the oil that comes out here. Gas is captured in these bags. And here's shale oil made in those reactors. See how light it is, about 33 degrees API gravity. But it's not perfect. It's not perfect because the kerogen has sulfur in it. This still has to be hydrotreated in refinery, even though it's only 1 centipoise in viscosity. This is the carbon number distribution. Compared to the Fisher assay oil that has all these higher carbon numbers, this does not. It has nothing past gasoline, jet, and diesel. Here's the Israeli shale oils, all made from the same source rock, and yet they're very different. This one heated a little bit higher in temperature. This one heated lower in temperature and slower. This one heated very slowly at lower temperatures yet. You can see you can change the product composition dramatically on the fly just by controlling your heating rate and pressure of the subsurface. So how is it that you're able to make such an incredibly light, optically clear product? What happened to all the carbon? Well, the carbon stays behind on the rock. This is the pre-pyrolysis oil shale and the post-pyrolysis oil shale. You can see the grains are very similar, but they're now black. Now, the subsurface energy balance basically consists of heating the rock, heating the water that's in the rock, and heating the kerogen. Let's say that that's 1 unit of energy required. Let's look at the energy out. So here's the energy in the 1 unit. Energy out consists of 2/3 is oil and 1/3 is gas. It's roughly at the face of the wellbore 6 times as much energy out as energy in. But this assumes that you haven't lost any energy in your heaters. And so if, for example, you're using molten salt, this thing would only be like 5 to 1. And if you're using electricity, it would only be 3 to 1. Now, the important thing about natural gas is that not all natural gas is created equal. The natural gas from Tamar is 99% greater methane, virtually pure methane. But the natural gas from the in situ conversion process is only about 34% methane. It has, however, some more valuable products in it. It has C2 to C4. That is, it has ethane, propane, and butane, essentially liquefied petroleum gas product. And it has hydrogen. Hydrogen is very important because it's much more valuable than the other gases. It also has some bad things associated with it. It's got H2S, which has to be removed in the Klaus plant, and it has some carbon dioxide. But the basic point is that it has more valuable components than just methane. That's what comes in normal conventional natural gas. So if you look at it from an energy balance viewpoint, you have 1 unit of methane coming into the oil shale. This is the only input into the process, basically, natural gas, used for heating the oil shale. And what comes out? Well, of course, oil, 4 units of oil energy. And then you've got methane, 0.7, ethane, 0.5, LPG, about 0.5, and hydrogen, 0.1. Now, it's clear that if you're using molten salt, 80 to 85% efficient, and you have more than enough methane and methane to supply all your energy needs, and there's no need for supplemental methane. On the other hand, if you're using electrical power, then you're going to be short, because then this becomes a 2. You've only got 1.2 from your methane and your methane. You hate to use LPG. It's much more valuable than the other gases. You hate to use your hydrogen. So in these cases, the electric case, it's really good to have a source of natural gas, pure methane, in the country. Here just shows the decoupling between the value of natural gas and oil, showing that oil is much more valuable on an energy basis than methane is. Starting around 2003, they started decoupling. Oil prices started rising, natural gas prices started falling, to the point now that on an energy basis, natural gas is only selling for a very small fraction of the energy in the oil. So it behooves us to use natural gas to make oil, because natural gas is selling at such a low value. And what that means for the economic balance is that for $1 of methane coming in, you have $18 of value in the oil coming out. And all these other gases, with the exception of methane, this adds up to $23 coming out. So for each unit of methane that's used, let's say, offshore, you have an economic gain of a factor of 23 if you have perfect energy efficiency. You would have an energy gain of 18 times using molten salt. So our timeline to commercial scale is basically shown here. We've done the geological survey on our acreage. We're trying to start our pilot. The pilot will make between 500 and 1,000 barrels of oil. Then we'll go through a demonstration phase where we'll make about 2,000 barrels per day. And then by 2018, we will be scaling up to the first commercial facility, which is 50,000 barrels of oil per day. The reason for choosing this is because this is what the military uses per day, plus the aviation market in Israel. We've already drilled 6 appraisal wells on our acreage. Here's what the pilot's going to look like, vertical well pilot. And just in closing, so there are actually quite a lot of synergies between natural gas and oil shale. One synergy is that Israel has a tremendous amount of natural gas, and a tremendous amount of oil shale. It has the capacity to be a net exporter of gas and a net exporter of oil. What's nice is that natural gas is the best fuel for subsurface heating. It's the least expensive and it's the least carbon dioxide. But having the reliable gas supplies enables the oil shale development to proceed more rapidly. Now, as I was trying to show, the energy content and the economic value of natural gas can be multiplied many times by using some of it as a fuel for heating the oil shale. And hopefully the combination of Israel's abundant natural gas and oil can make Israel completely energy independent. Thank you.
Thank you, Harold. One question only.
What's the trace element content Canadian and nickel? What's the trace element content of nickel and
Sorry, only one question from here.
Yes.
Harold, what do you think is the long-term future difference between the price of gas and oil? Right now, it's very large.
Well, long term, we're going to see them come closer together. But we are in for a very, very long period of time where the price of oil will continue to rise. There's a real shortage of oil in the world, whereas natural gas is much more common. And it's not just much more common, but the methods of producing it have improved dramatically. The tight gas shale in the United States, particularly the tight gas shale development in China, keep the price of natural gas down. And then the stranded gas issues are being handled very nicely with these large floating liquefied natural gas platforms. Shell just announced its prelude FID. This is in 110,000 barrels of DOE equivalent. It's 488 meters long and situated off the coast of Australia. First of its kind, this is the thing that something like that should be used, I'm sure, a ton. It's going to open up all the stranded gases. So the future is that the price of gas will stay low, not quite as low as it is now. The price of oil will rise.